Okay. And Swaroop, I don't know if you can, look at the chat session to answer questions as we go along, or you can stop and people can ask questions. Stop at opportune times and people can ask questions. So thank you.
I don't naturally see the chat. I can pull it up. Okay, I will try to keep an eye on the chat, but if I don't, just unmute yourself and go ahead and ask a question. Okay, does this come across?
Yes.
Okay,
We can get started. Thank you.
Okay, welcome to this session. I am going to talk a bit about the summit and the frontier system at the Oak Ridge Leadership Computing Facility. I'm Swaroop Pophale. I'm from the Programming Models Group at the Computer Science and Mathematics Division at Oak Ridge. And this is going to be, Frontier still has a lot of stuff that is under NDA, but all that is available to us to share with the public. I'm going to do my level best to bring that information across. So this is the very high level outline of my presentation. I will briefly talk about the OLCF mission and our roadmap to exascale and what we have been doing on our path to exascale, and a little bit about the summit system. Now, it's been a while since it's been in production, and I guess most of you know about it, but I'm still going to go into the details. And then I'll talk a little bit about the frontier system. So what is OLCF? This is our leadership computing facility. This is the facility in charge of setting up our supercomputers and everything that goes around it. It is not as simple as just getting the processors and putting them together. It's about making space for them, arranging power for them, the cooling, and then when the system is up, we have to go into the details of how we're going to program on it. What are the different programming models that we can support? How are we going to basically, what are the parameters of even accepting the system after it comes on board? So we have been successful in setting up 4 such supercomputers, or Frontier being our 4th. But stepping back a little, what we do here, it's a national user facility whose mission is to enable breakthrough in science by fielding the most powerful capability of computers for scientific research. Most of the things that happen on supercomputers cannot happen outside or in a lab situation. These are enabling science to the scale that we can't even imagine. So this requires, like I said, infrastructure and user access to this computer. And there are so many security measures that have to be put in place for different types of users. We also have a separate limb which selects time-sensitive and national and projects that are very important to the nation. And we partner with sometimes applications or teams of applications with the liaisons on site, which help them use the system in a most effective manner, be it unraveling complex gene interactions or forecasting nationwide increase in human exposure to climatic events, or even extending neutron experiments. It's the goal of OLCF and all our supercomputers is to help solve the largest problems in science. That said, we have a long history of successfully setting up huge supercomputers. Here are the supercomputers that we have stood up over the years. In 2009, we deployed the latest upgrade to Jaguar, which became the world's most powerful supercomputer for open science at that time. Jaguar actually began its service in 2005 with a peak speed of 26 teraflops. The upgrade to Jaguar XT5 to 37K 6-core AMD Istanbul processors happened in 2009, which pretty much increases performance 70%. over its quad-core predecessor. And in this, that was our first foray into being the top of the top 500 list. So in 2008, a team led by Thomas Schoffas of the Swiss National Supercomputing Center actually ran the first application called the DCA++, which broke the petaflop barrier. And it reached up to 1.352 petaflops. And that was closely followed by applications like WSLSMS and NWChem at Oak Ridge. So then we stood up Titan in 2012. Titan was a hybrid architecture with Cray XK7 system with a theoretical peak performance of around 27 petaflops. It contained both advanced 16-core AMD Opteron CPUs and NVIDIA Kepler graphic processing units. The combination allowed Titan to achieve around 10 times the speed of Jaguar, but it was 5 times more energy efficient. So that was our biggest achievement at that time. Then we stood up in 2017, we stood up Summit. And now, late to 2021, we hope to stand up Frontier. And I'll go into the details of those next. So the Summit overview, it has a system peak performance of 200 petaflops. It is used for both modeling and simulation, a peak of 3.3 exaflops for data and analytics and AI, which is one of the bigger achievements of Summit. The system includes 4,608 nodes. It uses dual rail Mellanox EDR. I'll talk about that a little later. And it has a 250 petaflops IBM file system, which can transfer data at 2.5 terabytes per second. So we will look at the node in detail in the next slides, but it has 2 IBM Power 9 processors supporting 6 NVIDIA Tesla GPUs, and it has a 608 gigabyte of fast memory with 1.6 terabyte of non-volatile memory support. So back in 2018, it demonstrated its wide variety of balanced performance. But in 2020, the Fugaku system turned in the LinPack results of 415.5 petaflops, besting Summit by a factor of nearly 2.8. So, but even as of today, Summit still remains the fastest system in the US and still the number 2 worldwide. So this is what a Summit board or one node looks like. It is the it has a Power 9 processors and we Volta 100 accelerators that are cooled with cold plate technology. The remaining components are cooled through more traditional methods, but both the cold plate and the heat exchanger operate using medium temperature water, which has been very cost effective for the center to maintain than using chilled water that our older system used. The water used to come really chilled and then the temperature used to drop as it cooled the system. But then we found out that was a major power consuming activity. So we moved on to this more viable way of cooling our chips. Now let's look more at the node architecture in detail. So it has a coherent memory across the entire node. It has NVLink, we will talk more about it, and it has PCIe Generation 4 interconnects. So the Summit system has 3 types of nodes: the login, the launch node, and the compute nodes. The launch nodes is where the batch scripts or the interactive jobs will start their execution. And it's never a good idea to launch anything on the login node. So although the nodes are logically organized into different types, they all contain similar hardware. So this is beneficial because this eliminates the need to cross-compile when you're building on the login node. Since login nodes will have the similar architecture resources as the compute nodes, any test, you can run a smoke test on the login node and it's going to work the same way. This basically reduces the number of intervention required by the user to try and account for the different programming environment maybe, or the architecture on the execution nodes. Now let's look at the Power 9 processors in a little detail. So you have on a Power 9 processor, you have 22 active cores with one reserved for OS activities. And you have 4 hardware threads per core. So each of the Power 9's physical cores has, you can imagine, has 4 slices or hardware threads. So these threads provide simultaneous multi-threading or SMT support within the core. Now, 3 SMT modes are supported in Summit. So SMT 4, 2, and 1. What does that mean? In SMT 4 mode, each of the slices or the threads operates independently of the other 3. This allows for 4 separate streams of execution, if you may. Or you can imagine them as OpenMP threads or MPI tasks on each physical core. Likewise, in the SMT2 mode, pairs of slices work together to run tasks. Finally, the last mode, the SMT1 mode, there are 4 slices working together to execute the task or thread assigned to the physical core. But regardless of the SMT mode used, the 4 slices share the physical core's L1 instruction and data cache. So let's look at the GPU part of Summit. So each of the GPUs contains 80 streaming multiprocessors, or SMs as we call them, with 16 gigabyte of high bandwidth memory and 6 megabyte of L2 cache that is available to the SMs. The GigaThread engine is responsible for distributing work amongst the SMs, and the 8 512-bit memory controllers control access to the 16 gigabyte of HBM2 memory. There are also high memory nodes supported, and they have 32 gigabytes of HB2 memory. Now, these Volta GPUs use NVIDIA's NLink interconnect to pass data between the GPUs, as well as from CPU to GPU. So one new thing, unique thing about Summit was its Tensor Core support. Now, the Summit, each streaming multiprocessor on the GPU contains 32 double precision cores and 64 single precision cores and 8 tensor cores. So the tensor cores basically allow for mixed precision calculations. And the Tesla V100 contains 640 such tensor cores intended to enable faster training of larger neural networks. With each tensor core performs a matrix operation, say, for example, or like the one on the slides, B is equal to AB plus C with a 4x4 matrix. A and B can be half precision matrices, while C and D can either be half or single precision. So this enables for applications to get with better performance by reducing their precision. So we have certain publications come out of this. Where one was accepted at SC in 2018, while another, which is a Gordon Prize winner, achieved 2.36 exaOPS on Summit. So let's have a closer look at the Summit network. So the Summit nodes are connected to a dual rail EDR InfiniBand network, providing a node injection bandwidth of about 25 gigabytes per second. So the nodes are interconnected in a non-blocking fat tree topology. So what happens is this interconnect is like a 3-level tree implemented by switching to connect nodes within each cabinet, which is at the first level, along with director switches, which is the second and third level, that connect different cabinets together. It also supports adaptive routing, which is basically your packets can bypass congestion, and it allows for out-of-order packet delivery on your network. And this is basically so that there is a load balance between the different switches, and a single link is not too congested. So the SHARP, which stands for Scalable Hierarchical Aggregation and Reduction Protocol, builds switches, and there is lots and lots you can do. You can tune with the SHARP protocol. It enables hardware collective and port mapping, and it has support for collectives, small collectives, as well as all those heavy operations like barrier, broadcast, reduce, and all reduce. So coming to the Summit parallel file system and bus buffers, Summit is connected to the IBM Spectrum Scale file system, which provides 250 petabyte of storage capacity with the peak write speed of 2.5 terabytes per second. So every node has access to the same space. So you can support multiple modes of file writing, like single shared file, or you could even distribute a per rank file. So each say MPI rank can write to its own file without having to interrupt other writes. So Summit also has access to the center-wide NFS-based file system. This provides users with the project home areas, and it also has access to the high performance storage system, HPSS, for users and project archival storage. So the local node NVMe it has linear scaling with job size, and it is only shared by ranks on a node. So it's useful when you're running a single job, but you have to save this to PFS at the end of your job. So let's take a closer look at the Summit programming environment. So we have the PGI compiler for CUDA, C, Fortran. We distinguish between C and Fortran specifically because of LLVM Flang being a little behind, or a lot behind, than the Clang part. So here we distinguish between GCC support is actually via OLCF itself. We have a subcontract with the Mentor Graphics to bring up the support for programming models like OpenMP and OpenACC. And of course, the native IBM Excel compilers, which are, they have CUDA support, CUDA C, Fortran, OpenMP 4.5. Some features of 5.0, but not a lot. And they have full support for the OpenMP CPU part of things. Again, LLVM, which is more of a community-driven effort, has support as of now. The LLVM trunk has support for is going towards 5.1 OpenMP support. which is great. That is like the latest and the best for GPU support. So current debuggers and performance tools on Summit. So the main ones for debugging are DDT, Valgrind, and GDB, of course. The DDT is ARM DDT, which has advanced debugging. It's an advanced debugging tool used for scalar and multi-threaded and large-scale parallel applications. So on the performance tool side, there are a lot of specific ones provided by different groups. But I think the widely used and the most appreciated one is the NVIDIA Insight. So it provides developer tools for profiling any code that runs on the NVIDIA GPU specifically. So before that, it used to support NV-Prof and other things, but those are no longer, well, they are still present on Summit. You can still use them, but they are now kind of in the maintenance mode. No new features are going to be added to that. So if possible, applications should move to using NVIDIA Insight, because it basically, you can use it for collecting timeline of your application and detailed performance information, even about specific GPU kernels. So that is very, very helpful. And we've seen application benefit a lot from using NVIDIA Insight for, especially for GPU kernel profiling. So this is the numerical library support on Summit. Summit provides many software packages and scientific libraries pre-installed at the system level. So you must, in order to link these libraries, you have to, the user has to direct the compiler to the location. Usually this is, you can do a module show, module load. You can find out details using the module commands. And that is how you would be successful in linking and using these libraries. So let's have a closer look at the Summit job launcher, JSRun. So what is JSRun? It just provides an abstraction of a node with the concept of a resource set. That is the key concept here. So the resource set provides the ability to subdivide a node's resources into smaller groups. So resource sets should be created to fit the code requirement, how your application will execute, what it assumes in terms of maybe say ranks or OpenMP threads tasks. So like I mentioned, resource set is a subgroup of resources within a node. So under the hood, it is implemented using C groups. So you can execute, for example, execute n MPI processes with threads, and that manages placement. Node sharing with multiple executables is possible within a job by a single user. So it can work in multiple programs, multiple data, NPMD mode. And it can concurrently execute compute-intensive GPU-only jobs. And you can do CPU-only analysis and visualization. So there are different ways you could use multiple GPUs. These are some of the common scenarios. So each mode gives you different level of flexibility. So the simplest mode, you could be like one MPI rank or one thread per GPU. And then you have the next mode, a little more sophisticated, would be multiple MPI ranks share a single GPU. Or then you could have a single MPI rank using multiple GPUs. Now, this is one of the modes which I've seen more commonly used. They try to use the fine-grained parallelism within the GPUs to get as much performance as possible. So the more node level parallelism you can expose you can better scale your application and you can get better performance. So there's no harm in profiling your applications, finding the hotspots, finding ways to find concurrency intranode or internode, and then exploit them using the appropriate programming model. So what has Summit been doing? We have been supporting different applications that would not have been possible in the labs in any facility. You have to use simulation to go beyond that level of prediction or computation. So we have a deep learning for human system biology, which is looking at molecular interactions within the human cell that leads to complex traits of an individual. So which potentially could lead to diseases like Alzheimer's or chronic pain. So by learning these, we can provide a map or a better prediction of what might potentially go wrong with a particular sequence, or say a particular pattern within the human, the interaction based on the molecular interactions. The cancer research, the ORNL Health Data Sciences, in collaboration with the National Cancer Institute, supports implementation of a more advanced population-based cancer surveillance, which essentially is training computers with large volumes of data to read medical documents and extract important information out of it and apply it back to what potentially are the causes, or what is happening in these populations, and what could be done to mitigate this. The another big application is the plasma fusion, XGC, which is a virtual fusion reactor that models the behavior of plasma, the hot gas medium in which particles generate fusion energy. And the other combustion application we have is called Raptor. Raptor tries to capture turbulent reacting flows in propulsion and power systems, or you can think of it as how combustion takes place in a turbulent environment, like in your car engines. So the code is a fluid dynamics solver that incorporates the multi-scale and multi-physics processes at play in the different systems. The astrophysics application FLASH is attempting to accurately model nuclear burning that takes place in a supernova, which requires multiple scales of physics calculations, from large-scale hydrodynamics to small-scale particle interactions. And this is only possible because of Summit's huge compute capabilities. Last but not the least, the material QMC pack application. It studies the properties of materials using quantum mechanics equations. So all these applications enable simulations far beyond what were possible before to make accurate predictions. Now we come to Frontier, and all that we know we can tell at this point. So as we all know, Frontier is a partnership between ORNL, Cray, and AMD. It is set to be delivered late 2021, and we expect peak performance to be greater than 1.5 exaflop. So it would have more than 100 Cray Shasta cabinets. Frontier will open to full user operations in 2022, is expected. And it will be connected by the Slingshot network with adaptive routing, quality of service, and congestion control. As we all know, the pandemic has pushed some of the deadlines, some of the supply chains, and still it feels good to be able to meet the deadlines, even if we are struggling at this point. So this is the frontier node architecture. It has the AMD EPYC processor with 4 Radeon Instinct GPU accelerators. It is it is obviously geared toward exascale computing. It is fully connected with the high-speed AMD Infinity Fabric links. And it will have coherent memory across nodes with 100 gigabits per second injection bandwidth and NVM storage. Now let's look at the I/O subsystem. This is the most recent information that we have made available to public. So it'll consist of 2 major components, an in-system storage layer and a center-wide file system called Orion. Now, Orion will use the open source Lustre and ZFS technologies. Orion will employ Lustre technology that technologies that include distributed namespace, data on metadata, and progressive file layouts. Lustre for distributed namespace, data on metadata, and we'll have 40 Lustre metadata server nodes and 450 Lustre object storage services or OSS nodes. Now, each OSS node will provide 1 object storage target device called OST for performance and 2 OST devices for capacity, with a total of 1,350 OSTs system-wide. We estimate that Orion will be the largest and the fastest single-file POSIX namespace file system in the world. So Orion will comprise of 3 tiers: a flash-based performance tier of 5,400 non-volatile memory expresses, NVMEs devices, providing up to a 11.5 petabytes of capacity at peak read-write speeds of 10 terabytes per second, with more than 2 million random reads I/O per second. Now, it also has a hard disk space capacity tier of 47,700 perpendicular magnetic recording devices, which provide 679 petabytes of capacity at peak read speeds of 5.5 terabytes per second, and the peak write speed of 4.6 terabytes per second. So with more than 2 million random reads I/O per second. And lastly, another flash-based metadata tier of around 480 NVMe devices, providing an additional capacity of around 10 petabytes. So this is a, you must have, as you can see, it's a really heavyweight system. So what does the frontier programming environment look like? So from Cray and AMD, the left side of the slide, we expect to get the Cray programming environment, or CPE, which includes all the CC compilers for the C, C++, Fortran, plus some GCC support. So we expect Cray to provide profiling, tuning, and debugging tools that go with it. And they will be providing support for OpenMP and both MPI and OpenMP, which is optimized for AMD GPU Direct. Now, from the AMD ROCm programming environment, we expect the LLVM compiler to generate code for both AMD EPYC CPUs and Instinct GPUs. This is expected to support C++ and Fortran and have GPU offload support, HIP, which will is basically for converting CUDA codes that originally use the NVIDIA system to run on AMD GPUs. Now, other than the vendor provided, we also have other sources of support. From the ECP, that's the Exascale project, we have the LLVM enhancements, which are coming directly to trunk. And the expectation is that all these enhancements will be picked up by Cray/AMD, and they will add their own secret sauce to make it more performant. We also have Cocos and Raja and HIP support, HIP LZ, which is a HIP support for Aurora. And we will also have other MPI implementations and HPC toolkit and PAPI enhancement. So from the ALCF, OLCF collaboration, we will also have a pilot implementation, which might not be a full system support for DPC++ and SYCL for Frontier. And like I mentioned before, OLCF is also working to enhance GCC support for OpenACC, OpenMP, and Fortran on Summit and Frontier. So to summarize, the compilers offered will be Cray, AMD, GCC. The programming language and the model supported would be CC++, Fortran, OpenACC, only in GCC is planned. OpenMP across all, that means Cray, AMD, GCC. HIP from Cray and AMD, Cocos supporting all, and UPC only for Cray and GCC. So we have transition paths, like most applications have been using for Summit, have been using CUDA to get as close to the metal as possible. But their path forward is simplest way would be to use HIP, which is it's a small level of interaction. The API is supposed to be very similar to CUDA. There is nearly one-to-one correspondence, and you can. That is the way we see going from CUDA specifics to running on AMD GPUs. Again, we have a summary of this, but I think I can move on from here. So HIP, like I said, is an API developed by AMD to be able to port codes from AMD to NVIDIA. So this uses CUDA and ROCm under the hood. And AMD has developed a HIPify tool, which basically converts all your CUDA calls to corresponding HIP calls. Is it perfect? Not perfect. You would, after you HIPify, you need to go back and look at your code, but it does a really good job of getting you to the step 0 of having all your code in portable HIP. And we do have support in Summit to make the transition easier and better for users so that it does not come as a surprise when Frontier is up and running. These are the programming tools we expect on Frontier. Well, we have the ARM DDT. We would still have support for that, and we will have more of the Cray tools, and we'll have the ROC GDB and the Cray GDB, which will be the AMD and Cray versions of the GDB. At the system level tools, we have most of the same ones, but some more tools in terms of ARM map performance reports. And most of the all the ones in green are already on Summit. So applications have been using it, or at least have some introduction to it. Now, at the node level, ROCprof and ROC Profiler and tracers, these are still in development stage. We have to give them time to reach the same sophistication that we have expected from the NVIDIA tools, but we are very positive that they will get there. So what is the scientific library supported on Frontier? We see we will have the BLAS, LINPACK, SCALAPACK, SPARS, and FFTW. Again, most of these, except the query-specific mixed precision iterative refinement library, are already available. And also there are SPAC recipes available for a few of them, which will be deployed via ECP SDK, which is basically the software release from the ECP projects, which will support these. So now what is the timeline? What are we looking at out here? So the early access system for Frontier is called SPOC, which is already operational. It is both ECP and CAR applications and some other groups have access to this. And this is where you would try your code as though to get it Frontier ready. So each SPOC node, compute node, consists of about 64 core AMD EPYC Rome CPU with 2 hardware threads per physical core. And it has access to 256 GB of DDR4 memory and is connected to 4 AMD MI100 GPUs. Frontier will have the MI200s. The CPU is connected to all the GPUs by PCIe Generation 4, and it allows host to device peak and device to host data transfers of about 32 gigabits per second each. So the GPUs are connected in an all-to-all arrangement via Infinity Fabric, and it allows for a peak device-to-device bandwidth of 46 gigabits per second in each direction. And each compute node also has 32 terabytes of NVMe devices with sequential read and write speeds of around 6,900 Mbps and 4,200 Mbps respectively. So this was the SPOC system, and Frontier will be delivered late 2021. And we will run acceptance on it for the first half of 2022, which basically targets the different subsystems and makes sure that it is meeting the requirements that were in the contract to AMD and HPE. So we expect to give general access starting June of 22. So Insight, which is the limb that chooses project, which seem of national importance, or that particular thing will ramp up from Jan 2023, and they will get access to the system in 2024. So in the meantime, Summit is our start using Summit, start experimenting on the packages and features that are going to be available on Frontier, and experiment on Spark for those who have access so that you are Frontier ready. I would like to end.
So there was one question about Singularity support on Frontier in the chat session. I think the rest of them you answered.
Oh, okay.
Kind of about event scheduler. So.
Okay.
And then for folks here, I think during the ATPESC training program, you have access to Ascent, which is a mini summit, but you don't have access to Spark on the MI100 AMD GPUs.
Right. Spark is right now limited to a special class of users, but yeah. I don't see the question.
About the Singularity support?
I'm not, I don't have information on that, but I can find that and post it on Slack.
Okay. Okay, that would be good.
Okay. Sorry, I'm a little over time, but this is my last slide, which I wanted to summarize Titan Summit and Frontier. And as you see, the trend has been the peak performance. Obviously, we're going to exasflop, but the nodes are, the number of nodes has decreased in Summit, but increased again in Frontier, but it's still half of what were in Titan. And with that, I will end my presentation. Thank you very
Thank you,
much for
Swaroop.
attending, and hopefully
Thank
this
you very much.
gave you
And
some